Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Chair of Astronomy here at Foothill College, and it's a great pleasure for me to welcome everyone here tonight in the Smithwick Theater and everyone listening to us on the web to this first lecture in the 20th Annual Silicon Valley Astronomy Lecture Series. This has been going on for 20 years, and we're delighted that it's continuing. We thank the sponsoring organizations, the Foothill College Physical Science, Math, and Engineering Division, NASA's Ames Research Center, one of the premier NASA centers around the country, the Venerable Astronomical Society of the Pacific, now celebrating its 130th year, and the SETI Search for Extraterrestrial Intelligence Institute. All these organizations have outreach programs in astronomy, very much like the lecture series that this talk is part of. So it's my pleasure tonight to introduce our distinguished speaker who returns to us, having given earlier lectures, and that's Dr. Jeff Moore. Jeff Moore is a research scientist in the Space Science Division at NASA's Ames Research Center and a leader of the imaging team that explored both Pluto and Ultima Thule with the New Horizons spacecraft. He's been a member or leader of several other space mission teams, including the Galileo mission to Jupiter, the Mars Exploration Rover, and the Mars Reconnaissance Orbiter. His research focuses on the nature and evolution of the surfaces of the planets and moons in our solar system, including the role played by impacts, quakes, and volcanoes on other worlds. He has also worked at the University of Oklahoma's National Severe Storms Laboratory and at the SETI Institute, and he has given talks, popular talks, around the country on astronomical topics. So tonight he will be speaking about a very exciting and current topic, the exploration of the most distant object humanity has ever visited. Ladies and gentlemen, please help me welcome Dr. Jeff Moore.
Good evening, everybody. Well, thanks for inviting me back. I was here about 3 years ago talking about the New Horizons encounter with the Pluto system. I know that that's on their website, so if you want to hear my rantings and ravings of 3 years ago, you can find it on YouTube. Okay, so most of the stuff on this slide has already been discussed, so let's just dive right in. Okay, so the New Horizons mission was first funded in 2001. We built the spacecraft and got the certifications to fly a spacecraft that uses plutonium for its, ultimately its electronic source, and got it out to the pad and launched it in January of 2006. Let me briefly discuss the payload of the spacecraft. Now, I'm a geologist, so I can talk with some expertise on geological and geophysical matters, but then there's some things which are not my field, so you won't hear much about them. So let's first talk about the things which I do know something about, which are the data collected by the LORRI high-resolution imaging system, and then there's a combination instrument called the RALPH, which is both a medium-resolution but wide-angle color camera and the LISA spectrometer, as you can see they're described here. And they all ride right here on this package. There's also an ALICE instrument, which is a UV spectrometer, which I won't discuss much about. And then there's two fields and particles instruments, PEPSI and SWAP, which I won't discuss at all. And not my department. And the REX instrument, which is basically using our radio antenna as a passive radiometer for measuring temperatures and things like that. Okay, so here is the historical journey to what you could describe as the third zone of the solar system, where conceptually the inner zone is the terrestrial planets, the middle zone is where the gas giants and the ice giants live, and then this outer zone, which is now known as the Kuiper Belt. And we're currently, in the extended mission, we're exploring this region out here. Now, 4 years ago, we flew past the Pluto system, and again, as I said, we talked about that here in this auditorium a few years ago. Of course, it turned out to be one of the most remarkable places ever visited by a spacecraft. Pluto, as it turns out, is every bit as interesting as Mars is in many, many ways, and it has an equally interesting, or I should say somewhat interesting, moon of Charon, plus some small irregular objects, which themselves have quite the story to tell. And you may have already heard Mark Showalter of the SETI Institute talk about them, or if not, you should invite him and ask him about them. Okay, so this is the extended mission, and we do several things. We look at the distant, large, dwarf planets in the Kuiper Belt because we have a unique perspective to see them as we ourselves are out in the Kuiper Belt to learn things about their phase curves, and which tells us things about the natures of their surfaces and things like that. But having flown past Pluto, the only target we have so far flown very closely to is MU-69, which is informally known as Ultima Thule. Okay, so what kind of target did we go to? We went to what's called a cold classical Kuiper Belt object. And I know this is a little bit of a geeky diagram, but what it's telling you is that the cold classicals have fairly circular orbits as these things go. Also, their orbits are kind of down in the plane of the general solar system. They're not at high inclinations of the solar system like, for instance, Pluto is. And so we think, for that reason, they represent an original undisturbed reservoir of the most primordial material still left in our solar system. So what's ever there is the basic building blocks of the world we currently live on, or we are part of, as well as the rest of the solar system. And it's probably the reservoir for many of the rest of these objects which have been disturbed by various types of gravitational actions with other planets that we think are in the early solar system, that the gas giants might have moved around, and that would have caused all kinds of helter-skelter in the system. And so you would have gotten things like stuff being scattered out, as they say in dynamics parlance, and you would have gotten things transferred into what's called Jupiter family comets. And for instance, you would have gotten things like CG, which was visited by the Rosetta spacecraft, probably began life here, but ended up getting roasted and toasted in the inner solar system. Okay, now the Ultima Thule encounter was far more challenging than the Pluto flyby. The target was 80 times smaller than the diameter of Pluto. We had to do a 4 times closer flyby, requiring a lot more navigational precision. There was uncertain target location, so as you'll see in an upcoming slide, we had to actually image a belt of space, hoping that our target would be inside the belt so we didn't miss the target entirely. Now, as it turned out, after all the gnashing of teeth and the pulling of hair, explains my hair, that we actually hit the target right on target. Had we realized that it was right exactly where we thought it was to within 5 kilometers, we would have had a completely different, much more aggressive sequence of observations, because we would have known we could have gone right to it and taken a bunch of different pictures as we flew by. But since we had to take pictures of a long belt, we took fewer pictures to make sure that in case we were wrong about where it was, we would capture it within this zone of uncertainty that these belts represent. So if things weren't bad enough, it was also 4 times darker than Pluto, and of course it's further out in the solar system, so it receives a fifth as much sunlight, or a tenth as much sunlight, and of course we were operating reduced spacecraft power, and last but not least, the 2-way round-trip transmission time between us and the spacecraft and back was over 12 hours. Okay, so here is a simplified version of the flyby sequence itself, and it's more or less to scale. And you can see, as the top bullet says, we flew past the target this New Year's Day. The encounter velocity was 14.4 kilometers a second, which is about 10 miles a second. The heliocentric distance, that's to say the distance of the target from the sun, is 43.23 AU, which I think most of you know means it's 43 times further from the sun than the Earth is. As we were coming in on the target, we were still way back here on the left side. We were approaching it at an angle of about 11.5 degrees, and at the closest approach, we flew about 3,500 kilometers from the target. And as this bar suggests, this is so we knew it would fall somewhere in this space, and so we planned all these infrared observations, color observations, best resolution observations by imaging the entire bar and hoping that the target would fit right in the middle of it. As I say, by incredible good luck, it fit, in fact, right in the middle of it. Okay, so unlike the Pluto encounter, Ultima Thule was basically unresolved pretty much until 48 hours before the encounter. So it was just basically a dot, a pixel in our imaging system. So the first images that revealed its shape indicated that it was oblong. And that was a surprise because as we were looking at it as an unresolved dot, the brightness never changed. So people were really puzzled how it was possible if the light was not changing, if it's rotating, especially if it's oblong. Why doesn't it tumble end over end and become bright and dark as you see it in the distance? Well, it turns out it's doing a pinwheel. It's basically its axis is more or less pointing at the spacecraft, and it's spinning like this in front of you. So its brightness isn't changing, even though it's quite elongated, as you can tell even from these pictures. And to give you an example of how things were going the very next day, so this is now the New Year's Eve, we've gotten this sort of a resolution image, and we can begin to say things about its size. It was about 33 kilometers long, or 21 miles. And then on the very next day, our first image radioed back to the ground. You could actually resolve the thing, showed that it was in fact made up of two joined objects, which of course initially looked to us like this. And so, and you'll hear me refer to snow on several occasions in this talk. And so the snowman model was held close to our hearts for some time during the first few days. We were getting images down. But as we began to get more images down, I should tell you some of the things that before I jump to that, let's talk about the things you can see at the highest resolution just briefly. We're going to go over in detail about this here in addition upcoming slides. But so we named the larger component Ultima, and the smaller component Thule. That made sense after coming up with the name Ultima Thule before the encounter. This is the best image taken. It has a resolution of a little better than about 70 meters per pixel. So in principle, an individual picture element would be about a little smaller than a football field. So the very smallest things you can see, like maybe the craters over here, are probably like maybe 200 meters across. Early in the game, we speculated it might be formed by the merger of two planetesimals, and we will go into a discussion of why we still think that and the implications for that. Okay, as it was pinwheeling in front of us, we finally, in the last day of the encounter, got enough information to actually determine its rotation, and it rotates slightly less than 16 hours. Now, this image is interesting, and I'm going to let it run for a while. On the right here is what it looks like as you're running up on the target. But this is a version where we derotated it and kept it all at the constant size. So you see it's sharper and sharper as you approach. But the cool thing about this, it also gives you a sense of what its real shape is like. And so as you watch, especially this portion, the Ultima portion, you can see it doesn't really look so much like a sphere or like the bottom part of a snowman after all. It really looks very flattened. And that's, in fact, what's going on, as we'll see in the next few slides. Okay, here is a fake stereo view in the sense that we took two images, which are in fact stereo pairs, and simply did a little bit of CGI to interpolate between them to give the impression that it's rotating back and forth. But as you can see, when the head goes all the way down, the little craters become more noticeable, and as the head goes back up and goes back, it's blended back into the lower resolution images, the smallest craters disappear. But again, it gives you some sense of the overall shape and appearance of Ultima Thule. Okay, now for those of you in the audience who can cross your eyes and see stereo, here's your chance. Now I can do that, and I think they say statistically like a fifth of the audience can do that. So for those of you who can cross your eyes and see in stereo, don't need your GF Viewmaster or anything like that. This is your chance. Okay, yeah, you see somebody out there can do it. I knew that. I always get the wow from the people who can do it. And just for the record, this is the highest resolution view, and this is the next highest resolution view, and they're obviously taken at different times during the near flyby, so you get a different perspective and thus get parallax and be able to see stereo. Okay, this is the latest and greatest shape modeling, so I'm going to show this to you first for truth in advertising. So you can see that they're both flattened, and Ultima is still flatter than Thule, although I'm going to show you an animation in a moment where Ultima seems thinner because it was an earlier version of what we thought its real shape was like. But this is the version that we're currently touting to the public based upon a lot of very hard work on the part of several different people using several different techniques to come up with an understanding of the shape of these objects. So it's really quite remarkable that they turn out to have this sort of flattened appearance and they're not simply spherical. And we're still trying to understand what does that mean about how the individual components form. Okay, here is the animation. It was made about 4 months ago when we still thought, let's see, there we go, where the Ultima component was a little flatter than it is now. But it both still communicates the idea we're dealing with a relatively flat, object, set of objects. Okay. So as you probably have already noticed just looking at the pictures that, Ultima is different than Thule. This is a geologic map that my colleague Oliver White put together. And for instance, it's clear that Ultima it has a much blander surface. There seems to be kind of less going on in some sense than there is on Thule. So we'll talk about both pieces in turn. First of all, I would talk about the crater counting that has been done. And we've had several groups of people do crater counting. And as you can simply see by looking at the pictures, there simply aren't many craters. This is a typical crater count for places in the outer solar system. This is in particular Pluto. And you can see Ultima Thule's craters are way the heck out here. So this crater slope basically represents the crater production function on an object which still records in production the earliest moments of solid surfaces in our solar system. And what's amazing is this region, the cold classical Kuiper Belt, is so unpopulated after it was first formed that essentially nothing has happened out there. It's, except for the single event which formed this large crater, which we've informally named Maryland, that, don't ask me, it wasn't my choice. That really, almost nothing has taken place, and it's really quite remarkable that something like this could survive and be preserved and represent the basic blocks of our solar system. Okay, let's talk a little bit about the apparent paucity of craters relative to the inner solar system. Now, this is a picture of Mars's moon Phobos, and before the encounter, we took this image, which was originally taken by HiRISE on the Mars Reconnaissance Orbiter, and down-resed it, and it added additional smear and reduced its signal to noise and did all those things so that it would represent an image which was identical in quality to this image of Ultima Thule. And so had Phobos been in our camera instead of Ultima Thule at the moment of closest approach, this is exactly what you would have gotten back to the ground. And this is informative because you can see there's far more kilometer, multi-kilometer sized craters on Phobos than there is on Ultima Thule. And Ultima Thule obviously just seems generally smoother, whereas you can see the undulatory landscape of Phobos. Also Phobos and Ultima Thule are lit similarly by the sun in these examples. So literally you can compare and contrast what something orbiting Mars looks like versus an object, and this object is in fact bigger than Phobos because he's also scaled it to the same size. To emphasize this point about how these two different locations of the solar system are really radically different. Okay, let's talk about some possible roles of collisions on Thule and how that might affect their tectonics. Okay, there's a plateau region right here. It's marked here as PM on this map that sticks up high, and we're asking ourselves, is this an uplifted block, and is it an uplifted block caused by either the impact of Maryland, or is it an uplifted block caused by the merger of Ultima with Thule? we don't know, but it's something we're thinking about, trying to consider what it might possibly be. And we also see there's these grooves here, and here they are shown in the map, as well as the neck itself. And we're wondering if it's one of two things, either these grooves and the other features, such as the plateau, are a consequence of the two lobes simply coming together, or are they, in fact, post-merger stresses on the neck that are expressing themselves in the form of fractures. So the fact that the two objects can retain their shape, and using some simple calculations about the tectonics of the two objects, we're able to do certain things, such as determine the minimum mechanical strength of Ultima Thule. And so, for instance, we know that it takes at least several hundred pascals, which I don't expect people to carry in their head what a pascal is. So I picked a common material most people had a chance of walking on, which is fresh snow. So it's at least as strong as fresh snow or stronger. And it also probably has a density on order of half a gram per cubic centimeter, which is half the density of water. And that seems to be typical for the density of comets as well, including comets we've investigated in the inner solar system. So those things all are consistent with the idea that Ultima Thule is a comet-like body. Also, there are some retreating scarps, we think, or at least putative retreating scarps. These features I've marked out these black arrows, and here you can see them here with this Hatcher marking here. Here's an example of retreating scarps in the south polar region of Mars, where solid carbon dioxide is subliming away in the spring as the sun comes back out and causes these interesting cuspate scarps, and we think that these features resemble that. We think that if in fact it is due to sublimation erosion, that the likely volatiles are either nitrogen or carbon monoxide or else methane. All three of those we have good reason to believe are abundant, at least in the primordial texture, outer surface of Ultima Thule. And they are all, even though Ultima Thule is way the heck out there and it's really, really cold, it's less than 40 degrees above absolute zero, so it's like 35 degrees absolute zero, or that general vicinity. That even still at those extremely low temperatures, that in timescales of a few 100 billion years, all these volatiles I just mentioned would have sublimated away, so these scarps are not still growing, they are basically stalled out. That probably that refractory material, by refractory I mean stuff that isn't volatile at those distances, and almost everything else is involatile at that distance, such as water ice and carbon dioxide and so on. So a lag formed and has prevented further erosion. And the last but not least, the possibility that the real culprit in all this was methane is the fact that it's dark, because methane, unlike the other gases, when they're exposed to radiation, the methane molecules recombine themselves into larger and darker and more refractory compounds. And so as these darker, less volatile compounds build up on the surface, it shuts the system down. And last but not least, if in fact it turns out to be due to sublimation erosion, it also implies that at least Thule is probably onion layered. And we've seen examples of onion layering in the comets we've explored in the inner solar system. Now, the reality is we're going to have to wait till someone flies out to Ultima Thule again with a rendezvous mission or another object like it to see if, in fact, these things are really onion layered. But at least it's tantalizing evidence that that's the case. And also, there's the whole story of what are the bright deposits. You know, the neck region itself is especially bright, and all the depressions, in fact, seem to be bright. And there's kind of two possibilities we've explored. There's always undoubtedly some, as you can see, something else which you probably haven't thought of. One is that it's simply downslope movement of fines, and the fines, that is to say, finely ground material is simply brighter than coarse material, and that's what makes it brighter. The other possibility is that there is volatile migration of the most volatile ices that might still be outgassing, and they collect in the local cold traps. And to test those ideas, here it's a model done by my colleague Orkan Umaran, who I work with at Ames, showing how stuff, in fact, does go, quote, down slope or downhill and collect in the neck. And this is a model done by James Keene at Caltech, which shows the regions which over a Ultima Thule year where the coolest places are. And once again, these parts of the net qualify as being cool net over the year. Okay, there's also on Ultima aligned pits, and here the arrows are pointing to a few of them, including some bright patches coming out of them. And we ask ourselves, are these collapsed pits formed under a fissure? Perhaps they're associated with some kind of outgassing or even mild explosions. We're not sure. The people who did the crater counting counted these as if they were craters, and even adding them into the crater count still didn't have any appreciable effect on the extremely old age of Ultima Thule. And of course, you know, as I said before, Thule simply isn't like Ultima. Ultima is just not like Thule. So Ultima, as you can see, is made of what seems to be a series of discretely bordered, similar-sized low mounds. We're not sure what it means. Maybe it represents some process in how finally flattened, or it represents the penultimate state of the subcomponents which made up Ultima were themselves similar size and came together. One idea, which people thought were crazy, but not so crazy, we didn't at least do a quick model, was that there is a short-lived, highly energetic radioisotope of aluminum, aluminum-26, which only exists for the first few million years after solar system formation. So we entertained the idea to use aluminum-26 to heat up the interior of Ultima and cause it to convect, and that's what caused the lump, similar to the lumpy surface you see on Sputnik Planitia on Pluto. But as it turns out, it doesn't work. That realistic parameters ain't happening. But as usual, once again, we will invoke some other process as, well, maybe will be the real explanation. Okay, also, Ultima Thule is really dark. This image, the color coding represents the albedo, or the brightness. And so something that has an albedo of 0.15, it means it has 15% the brightness, reflects 15% of the light it gets. And so as you can see from the color scale, that Ultima Thule on average reflects a little more than about 10% of the light it receives. And as I said, you can calculate for yourself what 1 over 42 squared is, how much sunlight it's receiving, and realize that it was quite the technical challenge to get good images of such a dim object under such low lighting. Okay, also Ultima Thule is really red, but it has a slightly less red neck, and being raised in Oklahoma, I can speak with authority on the subject of rednecks, and so. And it's amongst the reddest objects. It's in keeping with the redness we see of other cold classical Kuiper Belt objects, and it is amongst the reddest objects in the solar system. Okay, we have some composition results, some preliminary results. The ones which the spectroscopists are comfortable talking about is they have a possible detection of water ice. They also have a possible detection of methanol ice, and methanol is basically rubbing alcohol. It's the stuff they tell you don't drink because it causes you to go blind, unlike ethanol, which is a different story entirely. And again, as I stated earlier, it's red classical. It's got the right color and so on. And it has a spectrum that's similar to several other objects which we think come from the cold classical Kuiper Belt, but because, again, of the perturbances I discussed at the beginning of this lecture, have been scattered inward and form so-called centaur objects. And so some of these things are probably cold classicals that have now become parts of the centaur population. Okay, so one of the methods we used to get a final handle on the shape was we turned the spacecraft around after closest approach and let Ultima Thule fly in front of us. And as Ultima Thule swept across the star field, you could see where it was blotting out stars and use that to figure out the unseen shape. So this was yet another component of our work to try to get a handle on its actual shape. And here's a montage of the last 9.5 hours of observation for closest approach. And I can tell you now that data playback still is ongoing. We've gotten most of our data on the ground. We've certainly got what in NASA mission parlance is referred to as all the Class 1 or Class A objectives data sets are down. That's one of the reasons why I can sit and talk to you about this is because we have it, and it's been analyzed to the point it's no longer embargoed, so we can have a public lecture on the subject. But as you can see, the data some of the data will continue to come down well into next year. Okay, so let's talk a little bit about the origins of the binary. So you heard me suggest that these are probably two objects which merge together, but the question is how fast could they merge and still retain their original shape? So some of our colleagues who are not on the mission, but very capable modelers of something called SPH code, which stands for spherical particle hydrocode, and all that translates into is they have computers which can calculate the gravitational attraction between or amongst many, many particles. So you collect your many, many particles into initial shapes, and you send one of these shapes against the other, and you see how the particles interact with each other, mostly influenced by either the velocity that you impart on them or their gravitational interaction. So first we'll see what happens if you do a 10 meter per second collision. And that's, of course, a glancing collision, but you can see there's not much hope that they would stay together. So the next thing done was to do a 5 meter per second collision, and it's, as you can see, a little more promising. But the smaller target gets fairly messed up, at least in this particular simulation. We'll watch it one more time. Okay, so having done several of these runs, what becomes apparent is that collision velocities, at least in this particular model, have to be on order around 3 meters per second in order for the two objects to retain their more or less original shape. And so to give you a sense of what encountering something at 3 meters per second is like would be if you get up and stand in a chair and jump to the floor, you will land on the floor at about, very roughly speaking, about 3 meters per second. So that will give you a sense of how fast these things can come together. If they go any faster, you see they have problems. So the next question is, how do you form these in the first place? Well, other modeling by other people suggests you start off with particle clouds, and you just, again, play the same game at letting the particles interact with each other and collapse on each other. You can see that you'll fairly quickly generate various components, such as this one and this one either coalesce or they will orbit each other and still fling off. And here's a snapshot from different parts of this where you can see that you can get a central object with a number of smaller satellites which are bound to it. You can get spheres which will come together and disappear, and you'll also throw a bunch of stuff out. So probably this mechanism originally set up the arrangement where you would have at least a few large objects, Ultima and Thule and other things, and then how does it work out from there? Well, one hypothesis is that these things came together like you saw in the last slide until you had just basically two big objects left, and it was the gravitational ejection of the last few smaller things, which basically robbed orbital momentum from the two large objects, and then they finally came together, and that's how you see them as they are today. But there are other hypotheses, and currently the one that's most favored, at least by all the cool kids in astrodynamics, is this one, which is gas drag. And here they think that in the early solar system there is a lot of nebular gas still out in the region of the Kuiper Belt. And as these objects are initially co-orbiting each other, that as they plow through this breeze of extremely rarefied gas on timescales of a few million years, it robs the orbital momentum in the system and brings them together, and thus maybe in a surprisingly effective way of what's called hardening the cold classical Kuiper Belt binaries. And hardening is the word the dynamicists have come up with for getting into dock with each other. Okay, evidence that this, in fact, takes place fairly common is here is Ultima Thule, and here is CG, which was visited by the Rosetta mission, and here's some other examples of comets in the inner solar system, which you've had spacecraft fly by, and you can see that most of them that haven't, well, Ultima Thule, of course, has been roasted and toasted, but you can imagine these guys are simply roasted and toasted versions of binaries that came from the Kuiper Belt. But to show that there are, of course, a few objects which are also, we believe, originally Kuiper Belt objects, such as these two comets. They can also not show up in the non-binary form, but it's the binariness of comets is common. And so, so we think whatever process brought Ultima Thule together probably explains the common binary nature of many other comets and Kuiper Belt objects. Okay, the extended mission continues. Can we find another Kuiper Belt flyby target? Well, we hope so. We have enough power to last for another 15 years. At that point, we'll be approaching 100 times further from the sun than the Earth is. We're using our own camera, our own high-resolution camera, to image in front of us, taking long exposures, and we think we could find things as small as comet CG, which was this guy, which is only about 3 kilometers across and a tenth the size of Ultima Thule. Maybe as much as 2 months before we might run up on it, and if it's accessible, we can use the fuel that's still aboard the spacecraft to fly closer to it, and we have a canned sequence aboard the spacecraft which will try to collect data. So with a little luck, we'll get maybe at least one more, probably smaller object. So I'll conclude the formal part of this talk by asking you simply to think of New Horizons as a time machine that has transported us to the very beginning of solar system history, to a place where we can observe the primordial building blocks of the planets. And with that, I'll take questions.
You're probably one of the world's experts of a very esoteric thing, and that is cold objects way out in the farthest part of the solar system. We now have what seems to be a real interstellar comet coming in from the far outer part of some other solar system. Any comments on that?
No, it's just that it's interesting that it's the second one we've seen now in a couple of years, and we hadn't ever seen any before. I don't know if that's a consequence of a much higher quality ability to detect such things, or are we simply being showered by them, that they're all coming from some same source? I don't know. They so far don't seem to have compositions that are very different than our comets, from what I understand. Of course, I'm not a spectroscopist, so I'm not really the right person to answer. The first one that flew by was an extremely elongate object, so much so that people were wondering if it might actually be artificial, as in Arthur Clarke's science fiction trilogy, The Rendezvous with Rama. So the interesting idea. But so, and of course, in Rendezvous with Rama, they all flew in threes, as those of you who read those novels recall. So now we're seeing the second one, so who knows? Yeah. Sir.
Yeah, one of the things that I've read about or heard about is the meteor barrier in planetesimal formation. So does this tell us anything more about that problem and what a solution might be to it?
I'm sorry, I missed the operative noun.
Yeah, so the meteor barrier is that
the meteor barrier, yes.
Meteor
oh boy,
barrier.
Okay, now you're really getting to something which I'm not an expert on,
Okay.
which is how nebular stuff forms small objects. And I do know a person you could certainly invite to talk about that at length, and that's my colleague Orkan Umaran, who I mentioned earlier, who did the modeling of the local slopes on Ultima Thule. It's really an astrophysical problem. As I said, I'm a poor dumb geologist, so I can kind of only wave my hands about how it all comes about. And it's entertaining to listen to the astrophysicists talk about it, because they use so-called pebble accretion, and the word pebble means something completely different to geologists than it means to astrophysicists, apparently. So that being the case, I'm going to defer until Andy or Jeff invite Orkan to explain everything.
Okay, thank you.
Oh, yes, I'm sorry. Go ahead.
Why is Ultima Thule red?
It's probably red because it was once covered or had mixed in the soil a lot of methane. Methane is the gas that comes out of your stove, and you have a gas stove. But of course, in the outer solar system, it's so cold that methane forms in ice. But as solar radiation and cosmic radiation bombard the methane molecules, the molecules turn into bigger and darker and redder molecules. And so it slowly darkens and reddens as the methane's converted to larger molecules that are built up of the irradiated methane molecules. Does that help?
Yeah.
Okay.
What other stuff is in Ultima Thule?
What other stuff? Well,
What's it made
the
of?
two things that we know we could detect spectroscopically was water ice and methanol, which they say is like rubbing alcohol. And in both cases, it's so cold out there, those are both extremely cold and might as well be rocks at those temperatures. It's very likely that when Ultima Thule was formed, there was a significant amount of nitrogen, which you probably know is the gas which makes up most of our atmosphere. But again, when you get up to the Kuiper Belt, nitrogen turns into an ice. And in fact, on Pluto, there are whole glaciers and huge basins filled with slowly moving soft nitrogen ice. So we think probably nitrogen ice was an original constituent of Ultima Thule. And likewise, carbon monoxide, which is a poisonous gas to us, but it freezes and forms an ice similar to methane at these temperatures, these extremely low temperatures that exist in the outer solar system. And you could imagine other things like maybe some ammonia, maybe. Carbon dioxide might be there, dry ice, those things might be there. Ammonia and certainly carbon dioxide would be basically like rocks because it's so cold.
So I've seen so you had that series of images as the New Horizon probe was getting closer to Ultima Thule. I noticed that as it was getting closer, at the beginning it was getting closer at large intervals, and then it almost completely stopped getting bigger, the image.
Right.
So what caused that?
Well, that's actually the cadence in which the pictures are taken. And because the spacecraft, all the instruments are bolted onto the spacecraft, the spacecraft has to physically move to point different instruments at different targets or different things. Or if you want to take a color picture, then take a black and white picture and so on, you have to allow those pictures to be taken kind of one at a time. So there's a whole bunch of different observations which are kind of mixed in. Remember that one timeline I showed had the little bar and had a bunch of arrows or lines pointing to taking a picture of the bar as you flew past it? Well, because also the different imaging systems and spectrometers require longer or shorter times to take pictures, the interval breaks it all up. So the long story short is that it represented the unevenness in which we took pictures in order to accommodate all the other instruments on the spacecraft to collect data. And of course, we focused on trying to get good pictures during the basically hour we were close to Ultima Thule because, and that was when things were changing the most quickly for us too, was just there within that 1 hour. Before that, it was kind of off in a distance and it wasn't changing a lot. We had time to take more pictures.
Thank you.
Sure.
Hi, you may have touched on it in the beginning, but as far as the trajectory of the satellite, New Horizons satellite, how are you determining where its next location will be? Is that done with Earth-based imaging telescopes, or can New Horizons itself kind of survey its environment, its future environment?
It can do both.
And then the more broader question is there any sient you can do with New Horizons while it's not looking at?
Absolutely. As I alluded to at the beginning of the talk, we can look at Kuiper Belt objects which are further away. You can't resolve them. You can just see them as dots. But because we have a unique perspective on seeing them, we can see them, essentially at large phase angles from the view you get from the Earth. And what that means is that from the Earth, all the objects in the Kuiper Belt are essentially viewed the same way the full moon is. The sun's right behind you, and you're looking at the entirely illuminated face. But if you could fly past an object so you could see it half illuminated, you would see how the light behaves differently as you move past the object, not just because you're seeing more and more dark side of the object, but it would also tell you about some of the physical properties of the surface. So we're making those sorts of observations as we fly past these things, even you can't resolve them, but you can see the way the light changes and dims. And also we're close enough to see if we can detect rotation and things like that, or see if they might be also other binaries. So we're doing observations of objects that are distant to us, well, actually distant to both us here on the Earth, and they're distant to us from the spacecraft, but the spacecraft is much closer to them than we are on the Earth. And to your first question, well, we in fact found Ultima Thule first using Hubble images, which was the only telescope that was near the Earth, or on the Earth, in this case near the Earth, that could go dark enough and see things faint enough to find Ultima Thule. And we found only it and one other object, Ultima Thule size, that we had enough fuel on the spacecraft to fly to. But once we knew where it was, then we used a combination of data we collected from our own cameras and additional information that we collected from very fancy star catalogs to ascertain its exact location. And at the end of the day, we actually had it pinned down with a few kilometers, which is really quite remarkable. Even I was surprised we could get it so well, but we did. And in the future, since we now are in a realm where probably there aren't any objects bright enough to be seen even by Hubble, but we suspect there are smaller objects out there, and we ourselves can see those objects a couple of months before we come up on the target with our own cameras, and if they are accessible, we have enough fuel aboard to fly near them, and we have a canned sequence to operate and try to take some pictures of these smaller objects, which we might find on our own.
Thank you.
This is sort of a follow-up on what you were just saying. Has the New Horizons probe added anything to our understanding of the density of the Kuiper Belt or the number of objects out there, and do we expect it to before it runs out of power?
Well, absolutely. And the most important thing we did was look at the crater surfaces, look at the cratered surfaces, count the craters on first Pluto and its moon Charon. Now, Charon, unlike Pluto, hasn't been active for 4 billion years. So even the youngest portions of Charon, the smooth plains you saw in part of the pictures, are still very old. They're older than the mare, or the smooth, frozen lava surfaces on the Earth's moon by several hundred million years, or even 1 billion years. And even there we, see a real dearth of small craters relative to large craters. Impacts in the inner solar system are dominated by what's called a collisional impact population. It isn't just they're impacting of us, but they've been impacting of each other. And this impact of each other operates to basically very roughly produce 10 times as many things, half the size as objects that is the next object up in a category. So you get what's called a power law of 2 distribution of fragments, and that expresses itself in the many, many more smaller craters you see relative to large craters, for instance, on the moon or Mars or on the Earth. In the case of the Pluto system, we see far less small craters relative to large craters there than we do here in the inner solar system. And we think that indicates that the Kuiper Belt really doesn't have a lot of intercollisional destruction of particles, causing the population density to rise. And so they're far enough and few between so that that they don't interact. And when they do occasionally strike something at all, they just kind of leave this record of their infrequency. And probably that's what's coming to make it, for us, surprisingly difficult relative to what we thought would be the case when we built the spacecraft now almost 20 years ago, is we anticipated we'd actually find more small Kuiper Belt objects to fly past than we have, and the search for other objects to fly by is itself a further indication of the relatively few number of small objects relative to large objects in comparison with, say, the asteroid belt.
Okay, thank you.
Already estimated when both craters will merge out?
We think they will never merge out. We think now that the two bodies have come together, they will stay together to the end of the lifetime of the solar system.
Okay, thank you.
You're welcome.
Hi, thanks for the talk. Thanks for the second talk, and my question is related to hoping that you'll be back here to make it a trilogy.
Me too.
So, in regards to looking for an object, I'm assuming that's happening concurrently with getting the data back, and we don't have to wait 20 months. And also, is the mission fully funded to do this search for the next few years? And ideally, if we find something out there, what's your hope that we would find?
Okay, so let me take those several questions. We are currently funded to continue to look for objects until the middle of 2021. And we're not waiting until all the data are down before we start looking. We're already looking. So in case we run into find something soon, in fact, we think statistically, based on what people think is the distribution of objects in the Kuiper Belt, or at least the cold classical Kuiper Belt, it's better to be looking now than later. So we are engaging in examining the sky in front of us in accessible space to see if we can find something, while interspacing those data coming to the ground with the data that we stored on our recorders and sending to the ground from the Ultima Thule encounter. We're going to have to write what's called an extended mission proposal to NASA next year. And if it is funded, we will probably get something on order of another 4 to 5 years to conduct scientific investigations, including continuing to look for new targets we can do a close-up flyby of. But that's going to be in the hands of whether we write a really good proposal and whether the review boards and the NASA bureaucracy believe the story we tell them.
Thank you.
Sir.
Thanks. As I look at the bottom object there, it reminds me of when I was a child and I would take some lumps of clay, separate lumps of clay, and kind of press them together. It looks like the bottom object is comprised of a lot of different objects that have been gradually merged together. So, first of all, is that conclusion correct? And second of all, why wouldn't the top object eventually merge in the same way and become part of a single body?
Well, your description is one that came to our minds right away for the same reasons. We also played with clay, like everybody else. Now, if you go back to the slides I showed a few slides ago about stuff coming together at different collisional speeds, you notice the stuff that comes together faster also tends to not retain as much of its shape. So in this scenario, you would imagine that the individual components which make up the larger body, which we're informally calling Ultima, came together at higher velocities than the final merger of this amalgamated shape, which is Ultima, with the final feature, which is Thule. So again, in this scenario, you could imagine this lower portion being built up from similar sized material coming together at 10 or 15 meters per second, something like that, or 20. Whereas the final merger of Ultima with Thule, again, if the models are telling us anything, are at very low velocities on order of 3 meters per second or something like that.
But that doesn't correlate with the demonstration you showed. At 10 meters per second, when the two objects hit, it kind of sprayed out into space.
Well, yes, but let's go back to get this one to work. Oh, it doesn't cooperate with you when you've. Let's see if we can make. Oh, come on. Here, maybe we'll get this to work by going. It doesn't like going backwards. Sorry, let's get it to catch up. Oh, here we go. Now can we make this work? Oh, there we go. Right, but if you have it, of course, that was also a glancing view, and there's a bunch of other simulations which I'm not showing, but you can imagine that if it hit head on, you could have ended up in a situation where it kind of looked like the lumpy snowman, which might be two of the blobs which make up Ultima. And certainly when you get to 5 meters per second, you can imagine that these kinds of collisions, as they evolve, again, depending upon the real mechanical strength of the material as opposed to merely the model mechanical strength, that this feature, when it finally settled down, could also look very lumpy. So velocities that are several times faster than the velocity we think was responsible for merging Ultima with Thule could have been the velocities in which the individual lumps came together to form Ultima.
And does it heat the objects and that's how they merge?
Oh, I'm sorry?
Does it heat the
No,
objects?
they're not being heated. They're emerging just because of their relatively low mechanical strength and just the interaction of their relative velocities and their self-gravitation, the individual particles.
Thank you.
You're welcome.
All right.
All right.
Let's thank Dr. Moore one more time.